welcome to the deep dive. You know, if you're like most people, you are probably, right now, enjoying seamless cellular service, maybe GPS guiding you somewhere, or perhaps even streaming this show over Wi-Fi.
Mm-hmm.
That feeling, that immediate connection, it just works, right? But behind it is this incredibly structured science, RF and microwave wireless systems.
And that's what we're diving into today. We've been digging through some really comprehensive textbook material on this, foundational stuff.
Yeah, back to the physics, the hardware rules, performance metrics.
Exactly. And our mission really is to kind of pull out the core ideas.
Cut through the complexity, what's the essential hardware, the physics, those surprising engineering trade-offs that, govern everything from your phone to, say, massive radar systems.
Yeah, and it's good to frame it right off the bat. These systems, they kind of do two main things, right? Communication, your phones, satellites, Wi-Fi, but also sensing radar and navigation systems.
Yeah.
But fundamentally, they all rely on this robust RF and microwave front end. That's the bit that handles the signal right at the boundary, between the electronics and the real world.
The boundary. So let's start right there. The antenna, the physical bridge.
Right, the antenna. It sounds simple, but it's absolutely critical. It's the component that takes a signal guided along, say, a metal wire or transmission line.
Like inside your device.
Exactly. And it launches that energy, transitions it into electromagnetic waves that travel through free space.
And crucially, it works the other way around for receiving, too. Physics is fair here.
Oh, absolutely. It's called reciprocity. The same antenna structure that works best for sending a signal also works best for receiving it. Saves engineers a lot of headaches.
Okay, so if you want to measure how good an antenna is, you need some kind of baseline, a reference point.
Mm-hmm.
And that leads us to this theoretical thing, the isotropic radiator.
Right, the isotropic radiator.
Yeah.
Now, you have to remember, this is purely theoretical. It can't actually be built.
Like a perfect sphere of energy.
Exactly. A point source radiating energy perfectly equally in all directions. It just gives us a mathematical starting point. If you know the total power transmitted, P and E CEVO, then the power density PDD at some distance, $3, is just PD divided by 4P or R22.
That $4 R2PD, that's the surface area of a sphere. So it's just energy spreading out.
Yeah.
The fundamental loss you always fight against.
Precisely. But real antennas don't do that. They focus the energy. They have gain in certain directions.
There's a catch to measuring that gain.
Yeah.
You can't just stand right next to
No,
it.
you definitely can't. You need to be in what's called the far field region. This is a really critical concept.
Okay, why? What happens if you're too close?
Well, if you're too close, you're in the near field. And there, the electromagnetic fields are messy. They're reactive, complex. They don't behave like nice, simple waves yet. All the math we use for gain, power density, beam patterns, it only works properly in the far field.
So the far field is where the wave starts acting like a predictable, flat plane wave, locally at least.
That's a great way to put it. Where the spherical wave looks like a plane wave to the receiving antenna.
So how far is far enough? Is there a rule of thumb?
There is. It depends on the antenna's largest dimension, let's call it $0, and the wavelength of the signal, lambda. You need to be at a distance, $3, that's greater than or equal to 2D2 divided by lambda.
2D2 lambda. Okay, that formula really highlights the difference between, say, a tiny antenna in your phone and a massive satellite dish.
Absolutely. Let's look at the extremes mentioned in the source. You've got low-gain antennas, like a simple half-wave dipole. Think old TV antennas or basic radio towers.
Right. Spreads energy everywhere.
Pretty much omnidirectional, at least in the horizontal plane. Its gain is pretty low, maybe 1.64 times better than that imaginary isotropic source. Good for broadcasting, but the signal drops off fast.
Okay, then you jump to the other end, high-gain antennas, the parabolic dishes. This is where you get that aha moment about scale.
Oh yeah. Parabolic dishes are all about focusing energy. They take that incoming spherical wave and use their shape to reflect it into a tight planar beam. The example given was a 3-foot dish at 10 gigahertz.
And the gain?
The gain is enormous. A linear ratio of 5,047. That's 37 decibels, 37 dBs.
Wow. Over 5,000 times the power compared to the isotropic source, effectively. That's serious concentration.
It is. But think about that far field formula, 2D2 lambda honors 1. For that 3-foot dish at 10 gigahertz,
Oh.
You need to be at least 183 feet away for the far-field conditions to even begin.
183 feet.
Right.
So to properly test or use that high-gain antenna, you need significant physical distance. High gain means narrow beam, and it means practical constraint.
Exactly. It's a fundamental trade-off.
Okay, so that signal, maybe highly concentrated, travels its distance, hits the receiving antenna, and it's probably incredibly weak by then.
Vanishingly small, usually.
Which throws us right into section 2, the receiver's battle, the battle against noise.
Right. Once that weak signal gets into the receiver electronics, it's immediately fighting against noise from everywhere. There's external noise.
Like from space, stars and stuff.
Yeah, galactic noise, atmospheric noise, even just the thermal noise from the ground the antenna sees. Plus, all the man-made stuff, motors, power lines, other transmitters. It's a noisy world.
But often, the real killer is the noise generated inside the receiver itself.
That's very often the limiting factor, yes. Internal noise, you've got thermal noise, just electrons jiggling around in the components because they're not at absolute zero temperature. Then there's shot noise, flicker noise.
So the receiver has to pick out that tiny desired signal from its own internal hiss.
Precisely. And we quantify how much extra noise a component adds using the noise figure, usually denoted F.
Noise figure, okay.
It tells you how much the signal-to-noise ratio gets worse as the signal passes through that component. And this leads to probably the single most important rule in receiver design.
The first stage rule.
The rule of the first stage. It comes from the math of cascading noise figures. Basically, the noise performance of the very first active component after the antenna, usually an RF amplifier, dominates the entire system's noise performance.
Why is that?
Because any noise introduced by that first stage gets amplified by all the subsequent stages. If that first stage has a poor noise figure or not enough gain, you've already degraded your signal permanently. You can't fix it later.
So job number 1,
Yeah.
get a low noise, high gain amplifier right at the very front.
Absolutely critical. Low noise figure and high gain. That sets the lowest possible noise floor for everything that follows.
Okay, so noise figure sets the noise level. Then there's dynamic range, which defines the receiver's usable window. What sets the top and bottom of that window?
Good question. Dynamic range is the space between two hard limits. At the bottom, you have the minimum detectable signal, the MDS. That's where the signal is just too weak to be reliably seen above the noise floor.
Okay, the quietest sound you can hear.
Sort of, yeah. And at the top end, you have the 1 dB compression point, or P1 dB. That's where the amplifier starts to saturate. It can't handle any more input power without distorting, and its gain actually drops.
So too quiet is bad, too loud is bad.
Right. Let's look at that low end, the MDS. How quiet are we talking?
Yeah, give us some perspective.
Well, if you assume room temperature, which is standard, and a typical communication channel bandwidth, say 1 megahertz, the theoretical thermal noise floor is about negative 114 dBm.
Minus 114 dBm. That's...
Yeah.
What is that in watts? Tiny, like femtowatts.
It's about 4 femtowatts, yeah. F times 10, 15 watts. It's incredibly small.
So when my phone drops a call in a weak signal area, it's not just that the signal is weak, it's that the random thermal motion of electrons inside the phone is actually stronger than the signal it's trying to receive.
That's exactly it. The noise floor is that thermal energy. And because you need to detect the signal reliably, the practical NDS is usually set a little bit above that floor. Typically 3 dB is above, so around negative 111 dBm in this example.
Okay, so that's the bottom limit getting swamped by noise. But the top limit isn't just simple saturation, is it? There's this other nasty effect, intermodulation distortion, IMD.
Ah, yes, IMD. This is a huge headache, especially in crowded signal environments. Think about your phone in a city. It's being bombarded by strong signals from maybe dozens of cell towers, TV stations, radios.
Right, most of which you don't want.
Exactly. Now, when 2 or more strong signals hit any component that isn't perfectly linear and no real amplifier or mixer is perfectly linear, they interact. They mix together and create new, unwanted signals. Spurious signals. These are the intermodulation products.
Okay, ghost signals generated by the receiver itself.
Pretty much.
Yeah.
And the ones engineers worry about most are the third-order intermodulation products, or IM3. These come from frequency combinations like 2F1 to PM-F22.
Why are the third-order ones so bad?
Because mathematically, they tend to fall very close in frequency to the original signals you do want. Often they land right inside your desired channel bandwidth.
Ah, so your filters can't get rid of them because they're right there with the signal you're trying to listen to.
Exactly. It's self-generated interference that you can't easily filter out, like static appearing right on top of the music.
Nasty. How do you quantify how well a system resists this?
We use a figure of merit called the third-order intercept point, or IP3. It's a theoretical power level extrapolated from measurements that indicates the system's linearity. A higher IP3 means the system can handle stronger interfering signals before generating significant IM3 distortion.
Okay, so we need a low MDS to hear weak signals and a high IP3 to handle strong signals without creating garbage.
Correct. And the range between those two limits, properly defined considering the IM3 products, gives you the spurious-free dynamic range, or SFDR.
SFDR.
Yep. SFDR is arguably the best single measure of a receiver front-end's quality. The formula is roughly text SFDR 23 times in dB terms. Maximize that range, that's the game.
Okay, let's take these concepts, antennas, noise, linearity, and see how they play out in big systems. Starting with radar. The basic radar equation for maximum range. That equation hides a really tough engineering reality, doesn't it?
No, it's brutal. The maximum range, Remax, is proportional to the fourth root of things like transmitted power and antenna gain squared. So, Remax...
The fourth root. Let's unpack that. What does it mean practically if I want to build a radar that sees further?
It means improving range gets very expensive very quickly. Let's say you want to double your radar's range, go from tracking something at 50 miles to tracking it at 100 miles.
Okay.
Because of that fourth root relationship, you don't just need double the power. You need to increase your transmitter power by $24, which is 16 times.
16 times the power just to double the range. Wow.
Yeah. Think about the cost, the size, the cooling needed for a transmitter 16 times more powerful. Or, alternatively, you could try to increase the antenna gain, but that requires much larger antennas, which have their own costs and complexities. It's why pushing radar range is such a challenge.
And what you're trying to see with the radar matters hugely, too. That brings in the radar cross-section sigma.
Right, RCS, sigma. It's a way to quantify the target itself. It's like the target's effective area. From the radar's point of view, how much of the radar's energy it reflects back.
So it's not necessarily the physical size.
Not directly. Shape and material matter a lot, but it gives us a number. A person walking might have an RCS of about 1 square meter.
Yeah.
A bird, much smaller, maybe 0.1001 lot square meters. An insect, tiny, maybe 10 of 5 square meters.
So that difference in sigma, it means a radar that can easily see a person might need, 100,000 times more sensitivity or power to see an insect at the same range?
Exactly. That 1R44 dependence in the radar equation works both ways. Smaller RCS makes detection exponentially harder.
Now, how does radar actually get its information? The sources mentioned 2 main types.
The simplest is continuous wave, or CW radar, sometimes called Doppler radar. It just transmits a constant frequency.
Like a police speed gun?
Pretty much. It's great at measuring velocity. The frequency of the reflected signal is shifted slightly by the Doppler effect, depending on how fast the target is moving towards or away from the radar. That frequency shift, 5 hours, tells you the speed.
But it can't tell you how far away the target is.
No, because the signal is continuous, there's no timing reference. You know how fast it's moving, but not where it is.
Okay, so that's a limitation. How do you fix that?
You use frequency-modulated CW or FMCW radar. This is much smarter. Instead of a constant frequency, it transmits a signal whose frequency changes over time, usually sweeping up and down in a triangle or sawtooth pattern.
Ah, so the changing frequency acts like a timestamp.
Exactly. When the reflected signal comes back, its frequency is different from the frequency being transmitted at that instant. The difference between those two frequencies, the beat frequency, is directly proportional to the time it took for the signal to go out and back, and that time gives you the range.
Clever. So the beat frequency gives range, and any underlying Doppler shift on that reflected signal still gives you the velocity.
Precisely. FMCW gives you both range and velocity. It's used in tons of applications now, like automotive cruise control.
Makes sense. Okay, let's shift gears slightly to modern wireless communication. The growth there has been just astronomical.
Phenomenal, yeah. The sources mention 20–30% annual growth rates, driven almost entirely by cellular and personal communications.
And the core idea that enabled that explosion was the cellular concept itself, right?
Absolutely. 2 key things. Using low-power transmitters to cover small geographic areas called cells, and then reusing the same frequencies in other cells that are far enough away not to interfere.
Frequency reuse.
Frequency reuse is the magic. It lets you serve vastly more users within a limited frequency spectrum. Combine that with the ability to seamlessly hand off a call from one base station to the next as you move.
And you get the mobile network we know today.
Exactly. And the move from first-gen analog systems like AMPS to second-gen digital systems like GSM, TDMA, CDMA, that was huge too. too.
Yeah.
Digital allowed for much more efficient use of the spectrum within each cell, more users, clearer calls.
And the sources talked about this vision of personal communication systems, PCS, like the ultimate goal.
Yeah, the idea of a wireless go-anywhere communicator, something that works seamlessly whether you're connecting via your local Wi-Fi, the terrestrial cellular network, or even directly via satellite.
Using satellites in different orbits, ILEO, MEO, GEO.
Right. Low Earth orbit, medium Earth orbit, geostationary orbit, building a layered network that gives you coverage basically anywhere on the planet. But remember, every single link in that chain, phone to tower, tower to network, phone to satellite, it all obeys the same fundamental rules of antennas, noise, dynamic range, and interference we've been talking about. Hashtag tag outro.
So it really boils down to this pathway, doesn't it?
Mm.
The signal starts guided, gets launched by the antenna, travels through space, getting weaker and weaker, hits another antenna, and then has to fight its way through the receiver's noise and linearity limits to be useful.
That's a perfect summary. From the antenna interface through the physics of free space, facing the gauntlet of the receiver's limitations, and finally enabling these incredible applications like radar and global communications.
Which leads to a final thought, something for you, the listener, to ponder.
Right. Think about that radar range equation. Again, range going as the fourth root of power. Now consider satellite communication. A geostationary satellite is way up there, about 35,860 kilometers.
That's a long way.
It's a very long way. At typical satellite frequencies, say 4 gigahertz, the signal loss just due to distance, the free space path loss, is enormous, something like 196 dB.
196 dB. That's a factor of trillions.
Pretty much, an almost unimaginable loss. Now, we know just cranking up transmitter power is really hard and expensive, especially on a satellite. And we know the radar range depends on power times gain squared, PT22. So the question for you is, how do engineers make this work? How do they design a system, ground station, and satellite to reliably close that link across 35,860 kilometers with 196 dBs of loss?
They have to squeeze every last bit of performance out.
Every fraction of a dB matters. Antenna gains, receiver noise temperature, which relates to noise figure, transmit power, atmospheric losses. It's called link budget analysis. Balancing all those factors we discussed, noise, gain, linearity, path loss, is what makes global satellite communication possible. It really shows how fundamental these RF and microwave principles are.